VIP. Let's kick it.
Hey guys, and welcome to lesson 5.7, Laws of Logarithms. So in the last lesson, we went over two basic properties of logarithms, mostly the first two that you see on your screen here. So whenever the base of your argument is equal to the base of your logarithm, then the answer is just the exponent here, or the exponent divided by this exponent, which is 1. The other rule that we came up with is that when we have a base that's raised to an exponent, which happens to be a logarithm, if the base of that logarithm matches the base of your power here, then the answer is just your argument in the exponent. We'll make note of two other basic properties. Remember that you're raising your base to some exponent to equal this argument here. So when your argument is 1, whatever your base is must be raised to the power of 0. So b to the power of 0 equals 1. So whenever you see an argument of 1, you know that the answer is going to be 0. Okay? And then basically coming from rule number 1, whenever the base of your argument equals the base of your exponent, again, you're just taking this exponent here of 1 and dividing it by itself. And if you're dividing both of these things by themselves, then your answer is just going to be 1. Another way to look at that is b raised to what power will give you b? Well, any base raised to the power of 1 will give you itself. Okay, so what we're going to do now is come up with a few more rules, but before we do that, let's kind of consider the value of each of these logarithms. Okay, so log 4 with base 2. Well, 2 to what power is going to give you 4? Or in other words, we can rewrite it as having the same base. So 4 is actually 2 squared, which means my bases are equal. I'm going to take my answer here as the answer to our question. Okay, and for the next question, 2 to what power will give you 8? And if you want to write it out, you can say that 8 is really 2 to the power of 3, and because our bases are equal, I can say our final answer is just this exponent. And finally, 2 to what power will give you 32, and if you follow the same pattern here, you'll know that the answer is 5. Now, let's note that we took our first term, which was log 4 base 2, and we added it to our second, which is log 8 base 2, and you'll notice that the value of those two things, so the 2 plus the 3 gave us 5, and 5 was actually the answer to that third logarithm, log 32 base 2. It also works with subtraction. Our largest log there, log 32 base 2, take away log 8 base 2. Well, those values were actually 5 minus 3, which actually gives us 2. And 2 was the answer to log 4 base 2. So if we generalize these results, we can come up with the product law of logarithms and the quotient law. So what we're noticing in both of these cases is that so when all the bases are the same, and we're adding the logarithms together, notice that we have a 4 and an 8 as our argument, and when we multiply those two things together, we get 32. So that's where the product law comes into play. When you're adding two logarithms together with the same base, you can multiply the arguments together to give you log of m times n with that same base b. Same idea for quotient. So when you're subtracting two logs with the same base, you can actually divide the arguments to get your final answer. Okay, so log m base b minus log n base b, well, the bases are the same, so I'm going to take my arguments and divide, and that becomes the next logarithm. That becomes our answer. Okay, and as always, our base must always be bigger than 0, but it will never be equal to 1, as well as the arguments in both terms must be greater than 0. So what we'll do now is come up with one more rule before we go ahead and do some examples. If we take a look at y equals log x base b, and what we want to do is we want to write this in exponential form. So our base to the power of y equals our argument x. Now for our next step, we're going to raise both sides of the equation to the power of n. So if we go ahead and did that, we'd have x to the power of n, and then b to the power of y times n. Now we'll take the logarithm of both sides. So that'll look like log with base b, and our argument is still x to the power of n, and then log base b, and then b to the power of yn. Using the rules that we've learned in the last lesson, we can simplify the left side because the base of our argument is equal to the base of the logarithm. So our answer on the right side is just going to be yn. And again, yn can be rewritten as ny. Okay, so what we have now is log xn base b equals ny. And then we're going to substitute for y now, because from above, we stated that y was equal to log x base b. So if I substitute y, we have n times y. So notice that we've created the power law of logarithms. So essentially what happens is when you have a logarithm with an argument that has an exponent, one thing you can do is that this exponent essentially moves up front and becomes a coefficient. So n times that logarithm. Okay, so that is called the power law of logarithms. And again, the same laws hold true. Your base must be greater than 0 but not equal to 1, and your argument must be greater than 0. So what we're going to do here is express each as a single logarithm, and then we'll evaluate. So in part A, we have a lot going on in our argument here, so I'm going to simplify that. Okay, so we'll keep the log base 3. I'll change the argument, rewrite it with a fractional exponent, so this becomes 9 to the power of 5 over 4. And now, because we have a base 3 and a base 9, I think it would probably be best to change the argument's base also to base 3. So I'll change this 9 into 3 squared. So that's 9 to the power of 5 over 4. And if we were to simplify that, well, power to a power will just multiply. So 2 times 5 over 4 becomes 10 over 4. And if we were to simplify that a little bit more, that is actually 5 over 2. Okay, so what we notice now is that the base of the argument equals the base of the logarithm. So my answer must just be 5 over 2. In part B, we have two logarithms that are being subtracted, and they both have the exact same base. So when you're subtracting logarithms, you'll keep the base, and then we just divide the argument. So this becomes 48 over 3. So we end up with log of 16 with base 4, which is very convenient because I can actually write the 16 as a base 4, so 4 squared, and then obviously our answer will just be 2. Okay, for part C, again, we're adding two logs with the same base, so in this case I'm going to keep the base and then just multiply the arguments together. So this actually ends up being log with base 6 of 36. Now, again, you can rewrite it 36 as 6 squared, or you can just say to yourself, well, 6 to the power of what will give me 36? Well, 6 to the power of 2. Okay, and in this one, we have a few things going on. The first thing I notice is that this last term here actually has a coefficient of 1 over 4. So what I'm going to do first is actually use the power law and change that to an exponent. So I'll rewrite the first two terms, log 6 plus log 5, and then now this becomes log 81, and the argument has an exponent now of 1 over 4. And we can actually simplify that even further to say that 81 to the power of 1 over 4 is actually the same thing as taking the fourth root of 81, which ends up being 3. Okay, so we have 3 terms here. All are the same base. So I will keep the base, and I notice that I am adding the first 2 terms, so that must mean I'm multiplying the 6 and the 5, and then eventually I am subtracting the last term, so that answer will be divided by 3. So 6 times 5 is 30 divided by 3 gives us 10, and again, because we aren't writing an actual number here, it's implied that this is base 10, so 10 to the power of something will give me 10, and the answer here would just be 1. Okay, example 2. This time we want to write this as a sum or difference of logarithms. So I'll notice here that here's our argument, and we have x to the power of 3 being multiplied by y to the power of 4. So because I have something in the argument that's being multiplied, I can split this up as a sum of 2 logarithms. So I'll keep the base 2, and then we'll put one argument there, x to the power of 3, plus, again, log base 2, and we'll keep the second argument, y to the power of 4. Okay, and we can simplify that even further because each of these arguments have an exponent, and we'll use the power law here to change those exponents into coefficients. So I can simplify further and call this 3 times log base 2 of x plus 4 times log base 2 of y. Okay, let's move down to example B. So taking a look at the argument, I see division. So I'm going to take the numerator and I'm going to divide by the denominator. So that tells me I can subtract 2 logs with the same base, x squared z, minus log base 7, and then 49 y to the power of 5. Now you'll notice that inside each one of these arguments, we actually can split it up even further because we have x squared multiplied by z, and we have 49 multiplied by y to the power of 5. So I'll split up that first term as log base 7, and I'll take my first argument, which is x squared, and I'll add that to log base 7, and argument is z. Now this is where you need to be careful, because when we're splitting up the second term, well, we have a minus sign in front, so whatever work you do here, you should use brackets so that you'll remember to distribute the negative in the next step. So again, we'll split up, we'll keep our log base 7, 49, and then plus log base 7, and then the argument is y to the power of 5. So what we'll do in the next step is not only will we distribute this negative inside of the bracket, we'll simplify each one of these terms by using the power law. So using the power law, this becomes 2 times log base 7x. Not a whole lot you can do with the second term. It has no exponent. Well, the exponent there is just 1, so nothing will change in this one. So log 7 z minus, well, this is actually something we can evaluate. 7 to the power of something will give us 49. Well, 7 squared will give us 49. And then again, because we're distributing the negative, I'm going to put a negative sign there, and I'm going to say that this becomes 5 times log base 7 of y. Okay, and at this point, there is not a whole lot you can do. If you just want to maybe put it in alphabetical order of the arguments, but other than that, there's not much more to simplify. And that would be it. In example 3, we want to simplify each one of these expressions. So again, in my first term here, I see some exponent rules that we can do to actually simplify this argument first. So let's rewrite our argument here as x to the power of 5, and then x to the power of 1/3. Now, because I'm dividing with the same base, I can actually subtract the exponents. For our second term here, we have a power to a power. This actually becomes log of x to the power of 8. So again, I'll use exponent laws again just to simplify what's inside this argument here. So we keep the base, and then we're just going to subtract the exponents. So we're going to do 5 take away 1/3, and after you get common denominators, you should end up with 14/3, and then plus log of x to the power of 8. So now that we have we've simplified a little bit more, expressing this as a single logarithm becomes much easier. So again, the bases are the same, so we're allowed to do this. I'm going to keep the base, but I'm going to multiply our arguments together. So x to the power of 14/3 times x to the power of 8. Now again, using exponent laws, whenever you have the same base, you keep the base, and then you add the exponents together. So if you did 14/3 plus 8 and got your common denominator, you should end up with 38/3. And if you want to simplify one step further, you can actually take that exponent and bring it down as a coefficient. Alright, let's move on to part B. So in part B, I have two logs that are being subtracted, both with base 10. So I can rewrite this as one single log, x squared plus 4x minus 12, all over 3x plus 18. So what we can do in this case is factor both the top and bottom and see if anything will cross out. So what we can do here to simplify just a little bit more is cross out the x plus 6's, and what we're left with is just log x minus 2 all over 3. Okay, and one more example of this type, very similar to above. So again, we have the same base, so we will be dividing the arguments, 2x squared plus 7x plus 6 up at top, and x squared minus 4 on the bottom. Now you'll notice that we actually do have a complex trinomial here, so we'll do a little bit of a side work. The numerator of this argument here will be x plus 2, 2x plus 3, and in the denominator we have a difference of squares, so x plus 2, x minus 2, and again we can simplify by crossing things out, leaving us with simply log of 2x plus 3 all over x minus 2. In the past, we were given questions, or we've worked on some word problems where we've come to an equation that looks similar to something like this. So 7 to the power of x equals 400. Now, in previous lessons, the best way to tackle this question was to write both of those sides of the equation as the same base. But unfortunately, a common base here is not possible. There's no way that I can write 400 as base 7. So now that we know a little bit more of logarithms, what we can do to solve this question is take the log of both sides. So I would say log, and I'm going to choose any base that I like. I'm going to choose base 10 because that is the button on our calculator. Its default is base 10. So log base 10 of 7 to the power of x equals log base 10 of 400. Now, because I've taught you the power law, I can take this exponent x and move it up to the front as a coefficient. So this now becomes x times log 7, which equals log 400. And at this point, because it's x times log base 7 or log 7, I can actually divide both sides by log 7. And because I've chosen to use base 10, this is something that is easily done on your calculator. So punch in on your calculator log 400 divided by log 7, and you should end up with approximately 3.079.
Okay, so if you punched in 7 to the power of this, you should get something fairly close to 400. Now, it wouldn't be exactly 400 because I didn't write down all of the decimal places, but you'll get something very, very close to it. And that is it for today's lesson, and if you have any questions, as always, please make sure you ask in class. Take care, guys!